Hello, Algebra 1 students, and welcome to Topic 6, Exponents and Exponential Graphs. This is your 8th lesson, and this is actually your last lesson on graphing exponential equations. So we're just going to take what we've done the last couple classes and expand on that. Remember, we first learned what made a pattern exponential, that common ratio, and we saw some basic graphs. Last class saw us understand what made something exponentially grow or decay, and we also learned about the average rate of change. And today we're just going to finish off a few of those topics. So let's rock and roll. This first page is your opener, and there are two tables on it. For each table, you're going to need to fill in the outputs based on each equation. So for example, we have this y equals -1. Don't forget there's times 2 to the x power. So we need to take each x, substitute it in, do the math, and that will give us the output. All right. You're going to do that for each of these. And then, of course, you're going to graph all of those points. And once you have that done, you need to decide if this table and graph show exponential growth or decay. You can use your calculator to assist you on this, but you should also be able to do this without your calculator. It is up to you, but you should challenge yourself to try it by hand. Ready, set, go. All right, so you're back. So let's take a look at that math. I'm actually going to start with 3 and work my way backwards here just so we don't have to deal with negative exponents right away. So my y value here is going to be found by doing -1 times 2, and then here's my x to the 3rd power. PEMDAS says we do the exponent before the multiplication. We should know by now that 2 to the 3rd is 8, and -1 times 8 is -8. So this gives me the point 3, -8, right? 3, -8. Let's see, 3, -8. There we go. We have a few more to do. -1 times 2 to the 2nd power. We'll have a first power, 0th, -1, -2nd, and of course -3rd. And let's get these filled in. Anything to the first power is itself. I'm not sure why I skipped the second. I guess we'll have to go back to that. This gives us the point 1, -2. -1, 2 squared is 4. That gives us -4 here. I'll go ahead and graph those 2 points. 1, -2 and 2, -4. -1 times 2 to the 0th. We've learned in the past that anything to the 0th power is just 1. And so that'll give us -1 here. That's our y-intercept, I think. And now we deal with those negative exponents. -1 times 2 to the -2nd. We've learned over the last couple lessons that a negative exponent is going to take that 2 and give us the reciprocal 1/2 to the first. -1 times 1/2 is -1/2. So this gives me -1, -1/2. Left 1 and down a half. Continuing through, -1 times 2 to the -2nd becomes -1 times 1/2 to the 2nd. Or, some mental math, this is 4, -1 times that will give us -1/4. Alright, -2, let's see, -1/4 isn't quite to -1/2. I think it's right about there, give or take. Last one. -1 times 2 to the -3rd is -1 times 1/2 cubed. And I think that will give us -1/8, right? Remember, we know these values by looking at the positive versions and then giving us the reciprocal of those. So -3, -1/8. 1/8 isn't even to the 1/4 part, so I'm just going to have it sit on or just below the x-axis. Once we're here, hopefully you can see the trend of this graph. It looks like we start low to the x-axis and then we curl like so. And we have that typical exponential graph, except this exponential graph is below the x-axis, right? We might notice that this -1 was taking all of our positive values and turning them into negatives. So does this qualify as exponential growth or decay then? And this is kind of strange because our y values aren't really decaying to a number, right? In the past couple videos, we've said that a decay meant the numbers get smaller. And as you work down, the numbers do get smaller, they get more and more negative. But probably a better definition of decay is that our graph decays to a specific value, right? Last class we saw that the graph would decay to 0. It would sit on this right side just above 0. Well, if you look at this graph, it is actually not decaying anywhere. It's actually growing away from the x-axis. And so any graph that as you move to the right grows away from the x-axis, whether it's to negative infinity or positive infinity, actually demonstrates exponential growth. Let's try one more. Alrighty. I'm going to start with the negatives here. We seem pretty confident with those at this point, hopefully. And so I'm going to take that negative 3 and put it as a power. Now to work this out, I still am going to have the negative 1 out front. The negative 3 is going to flip my fraction. Instead of 1 over 2, it's going to become 2 over 1. But 2 over 1 is really just the number 2. So the reciprocal of 1/2 is 2, and then there's still a third power here. I took care of the negative, but not the third power. Alright, 2 to the third is 8, times 1 will give us negative 8. So this is the point negative 3, comma, negative 8. Putting this on my graph, negative 3, comma, negative 8 is right here. Alright, a few more. Negative 1 times 1/2 to the negative second means negative 1 times 2 to the second, which will give us negative 4. And negative 1, 1/2 to the negative first. The original reciprocal becomes 2 to the first, which is just 2. And don't forget that negative. So graphing these, negative 2, comma, negative 4, negative 1, comma, negative 2. Let's continue. When we use 0, it becomes negative 1 times 1/2 to the 0th, but anything to the 0th power is just 1. So that leaves us with negative 1 here, the point 0, negative 1. Actually the same y-intercept as the last equation, but certainly a different graph. I mean, the points are in completely different spots. Negative 1 times 1/2 to the first. Well, anything to the first power is just itself, so the negative version of 1/2 is negative 1/2. Let's do these last two, and then we'll graph the last 3 points simultaneously. Negative 1 times 1/2 squared. Now this one's a little bit trickier. We need to remember that when you square a number, as long as there is only multiplication or division inside that fraction, or inside the parentheses, we can distribute the square to each of those. What is 1 squared? 1 squared is just 1. What is 2 squared? Well, that's 4. And so negative 1 times 1/4 will give us negative 1/4. Let's try one more to make sure you understand. Negative 1 times 1/2 cubed. We're going to distribute the cube to both of these on the inside of the fraction. Negative 1 times, well, 1 times itself 3 times is just 1. 2 times itself 3 times is 8. Negative 1 times 8 is negative 1/8. This ends us with 3, comma, negative 1/8. Let's get these last couple points graphed. 1, comma, negative 1/2. 2, comma, negative 1/4. And 3, comma, negative 1/8. Hopefully this graph is starting to form a nice little predictable picture to you. It looks something like this. It's actually very similar to our other graph, except this one grew away from the x-axis and this one grew towards the x-axis. And so it probably won't surprise you that this is an example of exponential decay. This graph is decaying towards the value 0 or towards the x-axis. In fact, we should probably do a quick conclusion about which graphs show exponential growth versus decay, and I'll do them in different colors so you can see that they're different. If you have different colors, not a bad thing to do on your paper. Okay. Exponential growth are graphs that grow away from the x-axis as you move from left to right. They start around the x-axis and they grow up, up, and away. Or they could start below the x-axis, but they're still going to grow away from the x. Each of these are demonstrating exponential growth. What about exponential decay? Well, I bet you get it. We are going to decay down to the x-axis. This is a positive graph that decays, versus we have a negative graph which decays to the x-axis. Now, last semester we spent a long time on how to efficiently graph linear equations. This semester we're not even learning the full exponential equation, and so we're not going to spend too much time on being perfect with the graphs. Instead, we're really just going to look at a couple key features and use those to sketch a very rough graph. We're not going to be doing HK form. There is an HK form for exponential equations. But for now, we're going to focus on probably one of the most important concepts, which are the intercepts of exponential equations. We're going to look at the exponential equation y equals 3 times 2 to the x power. And all we're really going to do is put together parts A, B, and C, which I called 1 through 3, but you get the idea. And we're going to use those to create our graph, and that's going to be it. So we're going to start by finding the coordinates of the y-intercept. So again, that equation was y equals 3 times 2 to the x power. We need to remember that a y-intercept, of course, occurs on the y-axis. Here I called it f of x, but we know that means y. And if it's on the y-axis, that means my final point is going to be 0, comma something. I move left and right 0, but then I move up or down some amount, which means we need to take our equation. We want y to be in the equation, but I want x to be 0. And then, this is just like the math on the previous page, 2 to the 0th is 1, and 3 times 1 is 3. This tells me that my y-intercept then is the point 0, comma 1, 2, 3. Alright, let's do the coordinates of the x-intercept. So we're going to do the same thing up above, except now we know that the y has to be 0. I want to move left or right some amount, but I don't want to move up or down. We're going to take that same equation, y equals 3 times 2 to the x, but now instead of replacing x with 0, we're going to replace y with 0. So 0 equals 3 times 2 to the x. Alright, well, since we don't have x alone, we should try to isolate x. We don't know how to undo this, but we can at least undo the multiplying by 3 by dividing both sides by 3. This leaves us with 0 equals 2 to the x. When we've solved this before, we've said, okay, we should make the bases the same. So the question becomes, 2 to what power is 0? And that's a bit of a head scratcher, because 2 to positive powers keep 2 positive. 2 to negative powers turn 2 into a fraction. And 2 to the 0th is 1. In fact, we've discussed this a few times now. There is no solution to this. And if there's no solution, then what do you think that means about the x-intercept? That's right, there is no x-intercept. And in fact, for every exponential equation we do this year, there will be no x-intercept. We've seen that with plenty of graphs. Don't sketch this because I'm going to erase it, but we've had graphs before that have just sat along the x-axis on one side or the other side, right? Or they've gone below on each side, but we've never had an exponential graph that crosses the x-axis, and we will continue not to for this year. Alright, last but not least, same equation one more time. Y equals 3 times 2 to the x. Does this equation represent exponential growth or decay? Well, this equation is in the form of y equals a times b to the x power. And although this form is slightly new, we did learn last class that the b value, this guy that's attached to the x, is going to be multiplying by itself many times. And so that means that our b value is still the common ratio. And in fact, every rule that we learned last class still applies to this class. If b is greater than 1, and in this case, since b is 2, 2 is greater than 1, then that means that this is exponential growth. If you multiply numbers by 2 over and over again, they get very, very large. So this is exponential growth. All right, let's put this all together. Using the information, graph the equation y equals 3 times 2 to the x without using a table. Well, we need A, we have our point. We need to know B, and that we never get to the x-axis. And C tells us our equation is growth. Putting that all together, it tells us we are going to grow, and this doesn't have to be perfect here. It's up to you. You can be as perfect or as imperfect as you would like. It's going to grow, and then it's going to get closer and closer to the x-axis. And that's it. So we really did this just with one point and knowing that my equation was exponential growth. And that's as accurate as we have to be this year. Last but not least, based on our graph, what's the domain and range? Well, hopefully we are extremely comfortable with domain. That is our all real numbers. That's what x is allowed to be. Or you can think of it as the width of the graph. This graph is infinitely wide. You could also write that as negative infinity to infinity. The range of this graph can certainly be tricky. What y values are on here? Well, the y values, which measure the height of the graph, certainly seem to go up forever. So they go all the way up to infinity. What's the lowest they get? They get 3, then to 2, 1. Do they ever get to 0? Well, they don't get to the x-axis, so I don't think they get to 0. In fact, that's why we say that the y's are strictly greater than 0. Not equal. There's no equal to like we did last semester, just greater than 0. Or another way to put that is we start at 0 and go to infinity. We have parentheses though because we never actually get to either of those numbers. Alright, moving on. We're going to conclude our learning today by circling back to the average rate of change that we covered last class. The average rate of change explains, on average, how steep a graph is over a specific interval. Now, we discussed very briefly the formula last class, except we didn't actually use the formula. Last class we had a graph, and on the graph it was very easy just to count how far up and how far over. Today, though, we're going to go back to our slope formula, which is extremely useful if we don't have a graph just to count with. So if you don't remember the slope formula, you might want to write it at the top of your paper. Our slope formula is y2 minus y1, and I always put those in parentheses. I'll zoom in here, divided by x2 minus x1. And although there's nothing wrong with that formula, it's going to get less and less common over the next few years for you guys to use these tiny little numbers we call subscripts. And so instead of using those, we're going to use function notation. And the way we use function notation is we're going to have a couple points, right? In this slope formula, we had the point x1 comma y1, and we also had the point x2 comma y2. Well, now instead of those weird little numbers, we are going to do A for our first point and B for our second point. And we're going to use function notation. So if I have a function like this one down here, f of x, to find the output for an x value, we notate that as f of a. And same thing, f of b. So if I wanted to rewrite my slope formula, we would say f of b minus f of a over b minus a. And you will find that this is the most common way the slope formula is written as you move forward in your math classes. So although it's totally fine to use this, and this is the formula you'll get on your formula sheet at the end of the semester, you're going to see me use this function notation version more and more often, including today. So here we go. Average rate of change from 0 to 2. Well, these are both x values, so when we find that average rate of change, we're going to set up our slope formula. And I'm going to do that fraction line. In the denominator, we have the x's. I always like to put the larger one first, so 2 minus 0. In the numerator, I'm going to say f of 2 minus f of 0. Well, how do we find those? Did a nice little equal sign here. Bet you guys can do 2 minus 0, no problem. That's 2. Well, in order to find f of 2, and I'm actually going to color code this for you, we're going to use this equation up here. f of 2 means replace or substitute in an x value of 2. So it becomes 2 times 3 to the second minus, and then we need f of 0. We're again going to use that equation, 2 times 3 to the 0th. And now we just have a bit of math to do. Nothing too terrible, and you can always use your calculator to assist you. I'm going to work to the right since I have a little room. 3 squared is 9. 9 times 2 is 18. 3 to the 0th is 1. 1 times 2 is 2, divided by 2. And then we continue out. 18 minus 2 is 16. And although this is okay for your rise and your run, you might as well divide everything by 2 to get 8 over 1, or just plain old 8. The average steepness of this graph is 8. All right, well, what if instead of looking from 0 to 2, we looked from 1 to 3? Remember that this is the notation using x values. So this really means from x equals 1 to x equals 3. We have those closed brackets to say include the x values. Let's use our slope formula again. That's our average rate of change every time. F of 3 minus f of 1 divided by 3 minus 1. Okay, let's work this out. 3 minus 1, not too awful. F of 3, though, let's color coordinate, is going to be 2 times 3 to the third power minus, and then f of 1 is 2 times 3 to the first power. Working to the right, 3 to the third is 27, I think, and 27 times 2 is probably 54. 3 to the first is 3 times 2 is 6, divided by 2. 54 minus 6 is 48, divided by 2. And half of 48 is 24 over 1, or just 24. Notice this graph is much steeper on average than the first one, and that should make sense because this is a growth function. As we go more to the right, it's going to be steeper and steeper. 1 to go. From x equals 0 to x equals 1, we haven't done that one yet, have we? Nope. All right, so we use our average rate of change formula, f of 1 minus f of 0, divided by 1 minus 0. And by the way, I often get this question of, well, wait, what if I switched them? What if I wrote f of 0 minus f of 1 over 0 minus 1? Will I get the problem wrong? No. In fact, all you're going to do is just switch the signs. And we should probably just look at this in just a second. So let's work this one out and see what I mean by switch the signs. So f of 1, okay, this is 2 times 3 to the first minus f of 0, 2 times 3 to the 0th, divided by 1 minus 0, which is 1. Okay, work to the right a bit. 3 to the first is 3 times 2 is 6. 3 to the 0th is 1. 1 times 2 is 2 over 1. And this is going to give me 4 over 1, or just 4. Now, if you did the order backwards, well, we can cheat a little bit because I know what f of 0 is. F of 0 is what I did in green before, and that ended up becoming 2. And then f of 1, we also know. Okay, f of 1 is 6 over 0 minus 1. Working this out, the numerator becomes negative 4, the denominator becomes negative 1. You might say, whoa, that's not the answer we got before. The answer is negative. But is it? Negative 4 divided by negative 1, isn't that positive 4? If you think in terms of rise over run, this 4 over here meant up 4 to the right 1. This one means down 4 to the left 1. And I think if you trace that pattern, you realize it's the same pattern, just one is moving forward, one is moving backwards. Long story short, the order does not matter. Now, knowing that, why don't you guys try these next couple? Once you're done, you can unpause and see how you did. Ready, steady, go. All right. Hopefully you found some success here. I am going to work through each one, but if you guys all got it, feel free to fast forward by me. So we're going to do f of 0 minus f of negative 2 divided by 0 minus negative 2. All right, got to be careful of that double negative. F of 0 is going to use this function up here. If you substitute 0 in here, anything to the 0th is 1. So we're going to end up with, and I guess I should show these steps. We're still learning it, aren't we? So let's slow down a bit. So F of 0 will be negative 1 times 0.5 to the 0th minus, and then we have F of negative 2, which would be negative 1 times 0.5 to the negative second. Now, I happen to know 0.5 is 1/2, and so I'm going to do a little math in my head here. You could also have done this on your calculator, so don't stress it. 0 minus negative 2 becomes 0 plus 2. That's what happens when you have two negatives next to each other. So 0.5 to the 0th is 1. 1 times negative 1 is negative 1. I see two negatives here. Those are certainly going to become a positive. And then 0.5 to the negative first, or 1/2 to the negative second, will end up becoming 4. 4 minus 1 is 3, and I think we are left with 3/2. Sorry, that should be in green. All right, next one. Same idea. We have f of 0 minus f of negative 1 divided by 0 minus negative 1. Now we can cheat a bit here too, because we already did f of 0, and f of 0 just ended up becoming negative 1. So as we work through this, we know the one in blue will be negative 1. This will be a minus, and then in order to find f of negative 1, we'll do this in yellow just so I remember it, is going to become negative 1 times 0.5 to the negative first, all divided by 0 plus 1, just the slope formula. So we end up with negative 1 plus, see those two negatives again, plus, and then 1/2 to the negative first ends up becoming 2. 2 minus 1 is 1, 1 over 1, or just 1. Last one with an equation, from negative 2 to positive 1. All right, we've done negative 2 before. We know negative 2 ends up becoming 4. We haven't done positive 1 though. So f of 1 minus f of negative 2 divided by 1 minus negative 2. Okay. F of 1 I'll do in purple here. I think this one's not going to be as nice as the others have been, but hopefully I'm proved wrong. It's negative 1 times 0.5 to the first power. Oof, it's going to be a toughie. Minus f of negative 2 we've done. I did that in green before. That ends up becoming 4. And then this is 1 plus 2 in the denominator. All right, 1/2 to the first is 1/2 times negative 1. Half of negative 1 I think is negative 1/2. So we end up with negative 1/2 minus 4. And then 1 plus 2 I believe becomes 3. All right. Well, there's a few different ways to think about this. And I will give you a couple, well, I'll give you one way, maybe the way that I like to do it most. I'm going to go ahead and instead of writing dividing by 3, this is a cool trick here, dividing by 3 is the same thing as taking 1/3 of everything in the top of the fraction. So I'm going to go ahead and say 1/3 of negative 1/2 minus 4. All right, I'm going to use the space down below, and there's too much left to do, but I'm going to do this 1/3, and then in order to do negative 1/2 minus 4, we treat this as 4 over 1, and we give common denominators. Negative 1/2 minus 4 over 1, I'm going to multiply by 2 over 2 to give this 8 over 2. 2 steps left. We're going to end up with 1/3, and then this becomes negative 9/2, right? You have negative 1 of these minus 8 more is negative 9/2. And then we multiply straight across, negative 9/6, and maybe even reduce by dividing by 3 to get negative 3/2. Whew, there was a lot to that problem. Am I going to give you anything that terrible on a quiz or a knowledge check or a test? No, probably not. However, should you know how to do it all? Yeah. It's not too terrible. All right, last average rate of change for the day. Now, I've mentioned this many times. We try to look at any sort of mathematical concept from multiple viewpoints. What is it? How do we do it as a graph? We did that last class. How do we do this as an equation? Well, we just did 6 of those. And how do we do this given the data in a table? Well, it turns out tabular data is a little bit easier. Let's take a look. If we are asked to find the average rate of change over these intervals, and we know we have an input, output all the way through, let's work the same math as before. We're going to use that f of 0 minus f of negative 1 divided by 0 minus negative 1. Now, how do we do these? Well, the nice part is we have a table. F of 0 means an input of 0 gives us what output? Oh, that's right, 0. And same thing over here. F of negative 1 means an input of negative 1 gives us an output of 2, divided by 0 plus 1. All right, now it's just a matter of simplifying. 0 minus 2 is negative 2 over 1, and that's fine for an answer. You could also just put negative 2. 2 to go. We're going from an x of negative 1, right? That's how we read this, an x of negative 1 to an x of positive 1. Same setup, f of, and I'll keep going larger number first just to stay consistent. Again, the order doesn't actually matter, just be consistent, like so. Okay, f of 1 we haven't done yet. I'll do that one in yellow. F of 1 gives us an output of negative 6. Minus f of negative 1 we have done before, that's in green up there, divided by 1 plus 1. Alright, this looks like negative 8 divided by 2, or if you wanted, divide everything by 2 to get negative 4 over 1, or just negative 4. Last one. From x equals 1 to x equals 2. Same stuff. F of 2 minus f of 1 divided by 2 minus 1. Our friendly slope formula. Okay, f of 2 we haven't done yet. I'll do that one in purple. Gives me negative 24 minus f of 1 we did earlier in yellow. That's negative 6. I should be better with parentheses there, but I think you guys can follow along. Divided by 2 minus 1. Okay, cleaning this up a bit, we end up with negative 24 plus 6 over 2 minus 1. That gives us negative 18 over 1, or just negative 18. All right, so what did we do today? We're not quite done. There is one more challenge page, only a couple problems on there, but it's important to remember what our concepts were. So first, we were trying to focus on graphing y equals a times b to the x. First, we did that using a table, and we turned that into a graph. We also discussed there are 2 different ways to see exponential growth, and there are 2 different ways to see exponential decay. Then we actually graphed an equation without using a table. We did it with the y-intercept and knowing if there was growth or decay. We also just tidied up or finished up our average rate of change, discussing how exponential graphs are constantly changing their steepness, so we still need a way to measure the steepness, and that is the average rate. So to conclude class today, I have 4 practice problems for you. Your job is to go through and work all 4 of these. You are welcome to work with the people around you, and once you guys are done, you can unpause the video and see how you did. All right, first one. What's the average rate of change, so we know how to do that, on the interval of 0 to 1 of the function below with the larger y-intercept? Well, we have 2 functions here. 5 looks bigger than all the 3's, so I'm assuming f of x, but let's remember how to do this. So we are going to do, and I'll try to color code this as well, I'll do f of x in blue, and I'll do g of x in purple. The y-intercept of f of x equals 2 times 5 to the x. And I'll just kind of do this. We'll do the average rate of change over here at the end. So to do that, we need to remember that our y-intercept is always the point 0, comma something. We want a y value when the x is 0. And to find that, we replace the x with 0. So we find f of 0. 2 times 5 to the 0th. Anything to the 0th is 1, and so we end up with 2. My y-intercept for f of x is 2. The y-intercept for g of x, okay, is the same idea. 3 times 3 to the x. It's going to be something. It's going to be 0 comma something. So we do g of 0 equals 2, whoops, looking at the wrong equation, 3 times 3 to the 0th. Anything to the 0th is 1, and 3 times 1 is 3. Which one of those equations had the larger y-intercept? That would be g of x. So now that we've figured out which one has the larger y-intercept, we need to find its average rate of change on the interval 0 to 1. Now, since we're dealing with the equation g of x, I'm not going to do f here. I'm going to say g of 1 minus g of 0 divided by 1 minus 0. Zooming in a bit. G of 1 is going to be 3 times 3 to the first, and g of 0 will be 3 times 3 to the 0th over 1 minus 0, which is just 1. Cleaning this up a bit, 3 times 3 gets us 9. This is 1, so we end up with 3. 9 minus 3 is 6. 6 over 1 is just 6. So we had those multiple steps built in. First, determining the y-intercepts, then figuring out which one was larger, and then the average rate of change. Alrighty, second problem. What are the domain and range of the function below? Hint, sketch a graph. Well, I don't think we need a graph for the domain, right? All real numbers, we know that one. Or negative infinity to infinity. Alright, well, the range can be a little trickier. So let's take whoever wrote this as advice. Let's sketch a graph. To sketch a graph, we need to know, is this growth or decay? Well, the 3 is greater than 1, so it's growth. And then we also need to know the y-intercept. So my y-intercept here will be negative 2 times 3 to the 0th, negative 2 times 1, which is negative 2. So it's the point 0, negative 2. So here's my super rough sketched graph. 0, negative 2 is the y-intercept, and then it's growing. We know the graph isn't going to grow this way because that would go through the x-axis, and our exponential graphs this year don't do that. So what's the other way it can grow? It can grow like this. It can grow away from the x-axis as you move from left to right. So what does that make the range? Well, it looks to me like all the y values are below the x-axis. They're all going to be negative. And the way we say that are that the y's are less than 0. Another way to say that is that our graph starts almost at 0, but not quite, and goes down to negative infinity. Your teacher would probably wince if you wrote it that way, though, because we like to put the most negative number first, so that I'm sure they would prefer you put negative infinity to 0. All right. Which of the 3 equations below grows at a faster rate, and how do you know? Well, what determines how our exponential functions grow is the common ratio. That's what you're ultimately multiplying by lots and lots of times. And if you multiply by a large number, you're going to grow faster than a small number, right? Imagine you had $6 and your mom said, I'm going to multiply that amount by 2 every month. And your dad said, I'm going to multiply that amount by 10 every month. Which one grows faster? Well, of course, multiplying by the larger number. So let's take a look at the common ratios and see which one is largest. Our common ratio, and it looks like all of these are written in the form of a times b to the x power, is b. So 4 is my common ratio. Not bad. 2 is my common ratio. And so if it was just between f of x and g of x, f of x would grow faster because you are multiplying by 4 every time. And last but not least, 1/8. What a silly question. 1/8 is super small. Oh, but wait. Look at that negative exponent. I think this is actually a different equation in disguise. If I use the negative exponent on the fraction, it just reciprocates the fraction and gives us 8 instead of 1/8. And so in fact, when we write this exponential equation in our common form with a positive power, we can see that our common ratio is actually 8. So which function grows the fastest? That's right, h of x. All right, last but not least, find the average rate of change over this interval of the function which is exponential below. We need to remember which one is exponential, or what makes a function exponential, and that is, of course, by the outputs. So let's check these patterns. Looks like we go up by 2, and let's check this one. Looks like we also go up by 2, but through multiplication. Which one of these is exponential and which one is linear? Well, linear has a common difference. These numbers are all 2 apart. Their difference is 2. This table is linear. And so we wanted to find the average rate, which is exponential. Probably not this one. Oh yeah, we're multiplying by 2. That is good. This is our exponential. It has a common ratio of 2. All right, so we do need to find the average rate of change, though. We've done this a few times today. F of 2 minus f of negative 1, just getting the numbers from the interval, divided by 2 minus negative 1, and I'll work to the right. F of 2 can be found in our table. Oops, I said F, didn't I? This is called G, drat. It's not that important this year, but I try to be correct in my notation. We don't want someone to think, oh, they don't know the difference between F and G. All right, so G of 2 is 16 from the table, and then G of negative 1 looks like it's 2. Don't forget our double negative in the denominator becomes plus. 16 minus 2 is 14 over 3, and I don't think that reduces any nicer. You could go through and say it's 4.66666, but that's kind of gross because you have an infinite decimal, and so instead I'm just going to keep this nice, friendly fraction. All right, you guys are almost masters of the exponential function. We only have one lesson left. I know it's a long unit, but I think you've probably gotten a lot out of it. So yeah, one lesson left on exponentials, and that's going to be how to apply this to word problems and even a little bit of gasp real life. So thank you for sticking through this with me, and I'm excited to welcome you back to your last lesson, which is 6.9 next class.